Hi everyone, and welcome to my talk on nanophotonic optical phased arrays, opportunities and limitations. I'm Antonio Calalesina. I recently started a tenure-track professorship at Leibniz University Hannover after many years at the University of Ottawa in the groups of professors Laura Ramunno and Pier Berini. The interest in optical phased array technologies is growing as a result of growing interest on LIDAR technologies, as demonstrated by the trend of investments in the last years, which is shown in the graph. The theory to explain the behavior of optical phased arrays is well known. In fact, phased array antennas have been used for decades in the microwave regime to steer the microwave radiation. The working principle consists in imposing a phase gradient across the array. So the phase is progressively changed in a way that we have a phase gradient, and this is responsible for the steering of the radiation. The main difference between the optical and the microwave domains is in the characteristics of the pixels. In the microwave regime, the pixel is, for example, a microwave antenna, and microwave antennas, they can have ideal characteristics. So they are small enough such to be able to produce an array with a sub-wavelength pitch. They offer a 2 pi phase range and a controllable amplitude. In the optical regime, instead, an ideal pixel is not available yet. Many technologies have been proposed to realize optical pixels. For example, MEMS mirrors, spatial light modulators, waveguide arrays, grating arrays, photonic integrated circuits, and in recent years, metasurfaces. The main advantage of pixels based on nanophotonic metasurfaces is the fact that the meta-atom is sub-wavelength, and this means an array with sub-wavelength pitch. Here I'm presenting a plasmonic pixel, which is the building block of a reflect array metasurface. The pixel contains a dipole nanoantenna on a glass substrate, which is clear on the side view. The nanoantenna is covered by an oxide layer. We consider hafnia, then ITO, and finally a gold backplane. The pixel then works in a reflection. The sequence nanoantenna, oxide, and ITO forms a MOS capacitor, which is used to make the pixel tunable. In fact, by applying a voltage through the connectors showed in figure A, this is the applied voltage, it is possible to induce a current density variation over a thin layer of around 1 nanometer in ITO. The accumulation and depletion of free carriers over a thin layer in ITO is then exploited as the tuning mechanism to modify the phase of the reflection coefficient. We simulated the MOS capacitor via a numerical device and found the dependence between the applied voltage and the current density perturbation. Of course, we considered the breakdown voltage of the oxide. Once we know the range over which the current density changes, both considering depletion and accumulation, in this case we have an unperturbed current density of 3 × 10⁻20 per centimeter cubed, and the range is between 0 and 13 × 10⁻20 per centimeter cubed. We use this information to perform optical simulation. The figure on the right is the real part of the complex permittivity of ITO, when its current density changes between 0 and 13 × 10⁻20 per centimeter cube. ITO is simulated via a Drude model, where the plasma frequency depends on the current density. We observe that the wavelength at which the real part of epsilon crosses 0, which is the epsilon near 0 wavelength, blue shifts for increasing end perturbation. If you look at the behavior of our perturbed 1 nanometer ITO layer at a specific working wavelength, lambda c, we see that for a certain range of n perturbation, the perturbed thin layer behaves as a dielectric, and for the other range it behaves as a metal. Now we show the amplitude of the reflection coefficient when n perturbed change within the range that we showed in the previous figure. Please remember that the properties of ITO are fixed for the background ITO, and what's changing is n perturbed in the 1 nanometer layer. The green curve refers to the unperturbed system and identifies the main resonance of the nanoantenna at the working wavelength. Notice that this resonance is on the left with respect to the epsilon near zero wavelength of the unperturbed ITO, which is at around 2400 nanometer. This means that at the working wavelength, the unperturbed ITO behaves as a dielectric. And this is important because a nanoantenna immersed in a metal will not work. The epsilon near zero wavelength starts blue shifting by increasing n perturbation. See the red dotted line. This produces a reduction of the refractive index in the layer surrounding the nanoantenna and then a blue shift of the main resonance. See this green dashed line. This goes on until the ENZ wavelength, which is tracked by this red dotted curve, reaches the main resonance here. Once the ENZ wavelength crosses lambda c, the nanoantenna system changes. So up to here we were basically in a situation where the nanoantenna was immersed in a dielectric, and then suddenly the ITO 1 nanometer layer becomes metallic, so the nanoantenna is now surrounded by a metallic layer. So this transition from a dielectric environment to a nanoantenna surrounded by a metallic layer creates the large phase variation of the reflection coefficient that we will show in the next slide. So we actually see this jump, this sudden jump. So here the surrounding material is dielectric, and then here it suddenly becomes a metal. So the nanoantenna is now effectively bigger, so we have this sudden red shift of the main resonance. Now we focus on the behavior of the reflection coefficient at the working wavelength. By superimposing all the reflection coefficient curves shown in the previous slide, we observe the presence of a special behavior of the working wavelength. Here, in fact, the amplitude of the reflection coefficient is nearly constant, as we see in the figure on the right, as a function of applied voltage. This crossing point feature doesn't come for free, and it's the result of an optimization. So not only at the crossing point the amplitude is nearly constant, but also the phase goes through a large variation, which in this case is larger than 300 degrees. So what we demonstrated in the previous slide is a pixel with almost ideal characteristics, because our pixel now has sub-wavelength dimensions. In fact, the size of the pixel, the largest size of the pixel is 500 nanometer, and we are using a working wavelength of 1550 nanometer, and the propagation is happening in glass. It has also a very large phase, which is greater than 300 degrees, and also a nearly constant amplitude. So we want to validate our pixel design, which is shown in red, by simulating a phased array configuration. So to do so, I simulated an extended unit cell containing MZ pixels and applying periodic boundary conditions at the bottom and on the side. Of course, this simulation approach allows us to simulate only those steering angles for which the phase difference between adjacent pixels is 2 pi divided by MZ, because MZ is an integer. In the extended unit cell, and perturbed, so the perturbation of the carrier density is progressively changed to create a phase gradient across the array. Also notice that the presence of the connectors, which are necessary to enforce a voltage make possible only 1D steering for this type of array, so in the YZ plane. Here I show a simulation movie. Simulation movies are very nice to watch, and it's a particular characteristic of the FDTD method. In the movie we see a clear separation between the total field region, where the plane wave is injected, and the scattered or reflected wave region, where we have the reflected wave. It takes some time for the phase relation between the pixels in the extended unit cell to build up, of the order of 80 femtosecond, but once this phase relation is created, so we have a phase gradient across the array, we see that the reflected wave starts propagating at an angle. The excitation is at the working wavelength of 1550 nanometer, which is the wavelength at which the pixel was optimized. We now look at the phase of the reflected field to validate that the phase front is propagating at an angle. And actually the angle is exactly what we would predict using the generalized law of reflection. We need to look at the phase because, of course, the movie is not enough to validate our beam steering approach, so we need to verify that the phase front is actually flat. And here again, we quantify the quality of the beam steering by looking at the far field. So the phase front looks flat, but we want to be more quantitative, so I performed a near to far field transformation to calculate the radiation pattern. In the radiation pattern, we clearly see that actually our pixel design is good, because at the working wavelength where the pixel was optimized, so the working wavelength is 1550, grating lobes at this working wavelength are negligible, and the main beam is steered at a specific steering angle, which in this case was minus 15.5 degrees. However, for wavelengths which are slightly different than lambda c, long period grating lobes show up. So this tells us that our design is very sensitive to small variation of the wavelength, so it's a very narrow band behavior. However, this is intrinsic in the characteristics of this pixel, because a pixel which is very sensitive to 1 nanometer layer automatically is very sensitive to small variations of wavelength. In this case, since we are simulating an extended unit cell with delta, with the phase difference between adjacent pixels of 2 pi divided mz, the limited phase range does not play a role. Okay, and these grating lobes that we see here are due to the non-uniform amplitude. So in the next slides we will explain all the types of secondary lobes that we have in when we study the beam steering from an optical phased array. And in particular I will explain why we call these grating lobes long period grating lobes. So now we focus a little bit more on the effect of pixel limitation. So we mentioned that real pixels can be limited in phase, can show a non-uniform amplitude. And in this figure I want to show all the sources of secondary lobes in optical phased arrays. So let's start by the fundamental. So to realize beam steering, it is necessary to create a phase gradient across the array. So in this case we consider a phase gradient in the x direction. Okay, so this is the ideal phase gradient. Then we consider modulo 2 pi because in practical implementations there's no difference between modulo 2 pi and this phase gradient. And this is only ideal, so in practice we need to discretize it because our pixels have finite size, so we have a realistic phase profile, which is basically a discretized version of the ideal one. So the pitch, which is the distance between samples, so the distance between pixels, is the smallest feature in the array and is responsible for what we call grating lobes. So grating lobes were not shown in the previous figure. However, grating lobes arise when the pitch is larger than half the wavelength. And grating lobes are replica of the main lobe. So basically they have the same intensity as the main lobe. The array size instead is the largest feature in the array and is responsible for, in general, for side lobes. So when we look at a radiation pattern, there is the main lobe, and then there are some other big lobes which can be grating lobes or the other type of grating lobe that I'm talking about in 1 second. But then there are also all the others which are called just side lobes. So the limited phase range here creates another periodicity in the array that we call long period. Okay, so imagine we want to create this phase profile, and then there are some ranges where the phase is not available. Here is not available, and here is not available. So we introduce another periodicity, which is larger than the pitch, so we call it long period. And the grating lobes produced by this periodicity are called, we call them long period grating lobes. So when the phase range is lower than 2 pi, so we have this red band where we don't have a phase available to create our phase gradient. So in this case we need to find a strategy to fill this space where the phase is not available. So what do we do? In this paper, which is currently under review, we consider different compensation strategies to take into account the presence of this missing phase range. So one option could be just replacing by the maximum phase range available, which we call the maximum phase available for the pixel, which we call psi max, replacing by 2 pi, replacing half by psi max and half by 2 pi, or we can think, let's just keep the range where the phase is not available. So let's start again from 0. So we are in order to compare the strategies introduced in the previous slides, we calculate the radiation pattern by using the phased array theory. In particular, we only consider the array factor, and we set the radiation pattern of the single pixel f equal to 1. In this way, our study is independent of pixel properties and can be applied to optical phased arrays realized in many different technologies. In that case, however, the reader should use their own radiation pattern for the pixel by multiplying it by the array factor. In the paper, indeed, which is under review, a Python code is provided to study the radiation pattern for arrays with pixel limitations. So eventually the reader can use the Python code to input their own f for their specific system. Here I show the radiation pattern, in particular the array factor, as I explained, for varying maximum phase of the pixel And for two compensation strategies, the replace half and half and the skip strategies. The limited phase range is responsible for the creation of long period grating lobes, as explained. And their amplitude decreases for increasing psi max, as we see for increasing psi max. We highlight the highest long period grating lobe, and we actually provide the side lobe to peak ratio SPR as a measure of the beam steering quality. The black dotted line is the steered beam. In the case the pixel is ideal. So we see that it coincides with the actual steered beam for the non-ideal pixel, where we also have the long period grating lobes. In the case of the skip strategy, instead we notice that the ideal steering angle is different than what we obtain. And this is due to the fact that the skip strategy actually introduces a modification of the phase gradient. So it's not really a good strategy to use. In the same paper, we also studied the effect of a non-uniform amplitude. So based on experimental and numerical results, we introduce a variation of this amplitude around a value of 1. The variation may not be exact as what we consider here. So in real systems, the variation can be different than, for example, a sawtooth profile or a profile sort of like a jumping profile like this one. But this is just an example to introduce some amplitude variation and trying to understand how this relates to the amplitude of the long period grating lobes. In particular, the sinusoidal profile, for example, is inspired by the results that we obtained in the IEEE JSTQE paper, where a sine-like profile was observed. Again, the reader can use the attached Python code to input their own amplitude profile. So, of course, if this profile is too ideal, they can use their own amplitude profile and study the system with their condition. What's important to mention is that, for example, by comparing different ways of perturbing the amplitude, where we also change the intensity of the perturbation from 10% with respect to around 1 to 50% around 1. So an amplitude that changes between 0.5 and 1.5 across the phase range. We see that the sawtooth perturbation gives a better result in terms of SPR with respect to this other profile, and in the paper we also provide other amplitude perturbation profiles that we can use as a reference to understand how the amplitude perturbation affects the creation of long period grating lobes. And finally, to summarize, we also calculated an average SPR for steering angles between 1 and 90 degrees for different values of psi max and for different strengths of the amplitude perturbation. This is important because in the previous slides we considered only the effect of the limited phase range and only the effect of the amplitude perturbation, but it's important to consider these two effects at the same time because in a real pixel that's what happens. In this case, we show the results for a sawtooth perturbation and half replace compensation strategy, and we observe that there is that by plotting this average SPR, there is a region which is highlighted by these dotted red ellipse, where indeed we find some interesting performance, because we have psi max, which is around 270 degrees, and then we have a strength of the amplitude perturbation, which is up to 30%. And even though we have a limited phase range and a amplitude perturbation, which is up to 30%, we are able to see an SPR which is of the order of 10 to the minus 2. And this is interesting because 10 to the minus 2, since here we are talking about intensity, means that the intensity of the side lobe is 100 times smaller than the intensity of the main lobe, and this is enough for many real applications. So this puts us in the condition of saying, okay, our pixels, even though they have limitations from the viewpoint of the phase range and from the viewpoint of the flatness of the amplitude, they are still able to provide an SPR of 10 to minus 2, which is good enough for many real applications. So this is interesting for the realization of optical phased arrays. And with this, I conclude the presentation. Here I am again to say thank you for your attention, and I would also like to mention that research positions are available in my group. So if you're interested in computational photonics and optical design using high-performance computing, please feel free to send me an email, and I will be happy to discuss it with you. Thank you again. Bye.